Hi, everyone. Good morning and welcome to the first session at the Almadina track. For this first session, we will have Antón Rodríguez. He's joining us from Spain. Hi, Antón.
Hi, everybody. Bon dia.
Bon dia. And he will talk to us about schema management, the elephant in the cloud room. Welcome, Antón, and have a nice session.
Thank you very much, Bruno. It's a big pleasure for me to be in JNation today. In this session, we are going to speak about schema management, also about how to integrate on-prem data centers with cloud or clouds between themselves. So how to move data from one place to another one in a quite good scalable way. Let's introduce myself first. My name is Antón Rodríguez. I am a principal software engineer working in New Relic. Before than that, I was working in other big corporations like Inditex Group, like Vodafone, Orange, and many more. Specialized in building internal platforms, so developers inside those companies can use those platforms to build their own services and to solve business problems. I started with orchestration, then I moved to build API gateways, API platforms. In the last year, I've become very specialized in data streaming. So working with Kafka, Flink, Kafka Strings, Spark, and in general, the data in motion, moving data from one place to another one in near real time. Because of that, I am running now a community called Streaming Annotated. It started as a newsletter covering the last news about Kafka and the other platforms, and also what the cloud providers are doing in that particular space. So if you have interest in this topic, just go to streamingannotated.substack.com and you can join, receive those news and participate. It's a very welcoming community. I'll also organize the Java user groups in Vigo and Coruña that are in Galicia, very close to Portugal, very active on the community. So let's start what we are going to cover here today. It's how to load data to the cloud. So let's try something here. Let's start with the basis. So we have our producer application, okay? This can be any type of application. It can be a microservice, a monolith. It maybe even can be a database. Most of the databases now have some features called change data capture, which are able to all the changes in the database, expose them so you can move that data to other places. So thinking any application generating data. And what we want to do is to move that data to the cloud. So that may be any cloud and any storage in the cloud. So maybe it's a database, maybe it's an object storage. Things like BigQuery or Snowflake or AWS S3, it doesn't matter, okay? Our application just want to move information to the cloud. So what we can do here is to add or use the SDK provided by that storage. So some libraries in our application, and using them, just upload our data directly to the database or whatever service, so it can be consumed and used by other teams, other developers, or our customers. This is a pretty typical pattern you can see out there, but it also has some problems. The main problem I see is if we have slow connectivity for whatever reason between our producer and the cloud storage, things are going to be complicated. So we may have problems here typically, or here in the cloud. You know, the cloud sometimes fails, sometimes have problems. When that happens, we don't want our producers to be affected. But with this pattern, the only thing the producer can do is start to buffer all that data, maybe in memory, waiting to recover the connectivity, and once it happens, send it to the cloud. If the problem persists for a long time, in some point, our producer is not going to be able to retain that data and is going to have to discard part of that information, or maybe store it in an internal place. So once it has connectivity again, can start to recover and send that information. This is not good. It's quite challenging from the producer point of view, and it's very complicated. So some of the improvements to this I usually propose is to use a service like Kafka. But let me first cover the basics here. I know my drawings are not exactly the best out there, so I have also slides for you, but it's exactly the same thing. We have our producer sending data to our storage. Our producer needs to care about the connectivity, the storage, and the problems it may generate. So let's use Kafka to improve our scenario, right? So what is Kafka? If we see Kafka as a black box, is we have our producer generating data, and it can send it to this black box Kafka. And from here, we are going to have different consumers reading the data. So when I say data, it's wherever you want, maybe strings, maybe JSON files, maybe CSVs. Kafka really doesn't care about the format. So we send the data, and this is one of the benefits of Kafka, is going to be able to send that data to all the different consumers. So all of them are going to receive a copy of our data. If one of those consumers is slow or it has problems, the other consumers are not going to be affected. So the first benefit of Kafka compared with other systems like MQs and so on is the ability to decouple the consumers and the producers, but also the consumers between themselves. So if we have a consumer which is slow, having problems or whatever, the other consumers doesn't care about it because Kafka is able to make them independent. The other particularity or benefit of Kafka is when we send a message or data to Kafka, Kafka is going to store it internally in a log file. And once it's read from the other consumers, Kafka yet keep that file internally. So if we have now a new consumer, that consumer can choose to read from the very beginning and read that data, or can read just the newest, but you have that election. If one of the existing consumers, for whatever reasons, needs to reprocess the data, it can also do it. So it can come to Kafka and say, hey, I processed that message, but it was wrong, my processing, I need to redo it. So please send to me that message again, okay? So this is called the replayable log. And it's also a very interesting feature of Kafka compared with other systems. The third one is the capacity of Kafka to provide high throughput for the ingestion. So it's really fast persisting data. So our producers can typically send a lot of data and Kafka is able to store it very, very quickly. So our producers don't need to care. They only care to send the data to Kafka, and that's all they care, okay? So this is the Kafka as a black box. It's not a database, it's a place designed for data in motion, and the benefits are high ingestion, consumers which are able to consume, to read in an independent way, and being able to store the information for a configurable period of time, like 1 week, 1 month, or whatever you want. So that information is kept in Kafka to be reused if needed, or to be sent to new consumers if needed. Kafka provides even more features which are interesting. One of them is it's a distributed system. So we have our producer, and Kafka typically is a cluster of nodes. Those nodes are called brokers. So we have broker 1, broker 2, broker 3, and our producers can send data to broker 1. And if broker 1 is down, instead of sending to broker 1, it's going to send it to broker 2, and the system continues working. So we have that high availability. It's not only from the producer point of view. When we send a message to broker 1, we typically also to configure the broker to create a copy of that message, for example, in broker 2, and maybe even in broker 3. So this is the replica of our data. If we lose broker 1 for whatever reason, we lose it forever. It's not a big deal because we have yet a copy of our data in the broker 2 on broker 3. So also Kafka gives us the possibility to don't lose information, to don't lose our data, because it's replicated in different machines and in different places. So this is the Kafka architecture. What we have here is, as I said, the producer sending to different brokers and the information replicated to the other brokers. So we have our consumers reading from the broker 3, a segment, a partition called leader 3. If we lose broker 3 forever, our consumers can go to replica 3 in a different broker, and we are not going to lose that information. And that's a very important feature of Kafka. So let's see how we can use Kafka to upload information to the cloud. What we're going to do here is, again, we have the producer, but now instead of send directly to the cloud, the producer is going to send the data to Kafka. And now we have here our cloud with a storage. And what we're going to do is, from Kafka, read that data and ingest it in our cloud storage. So we have, for example, we can do it with Kafka Connect. Kafka Connect is a framework, it's part of Kafka. And basically, it gives you like default integrations between Kafka and different systems. You can think in every database out there, every object storage, or other brokers, and so on. So you don't need to code anything. It's just configuration. You configure what topics you want in Kafka, with what credentials you want to use, and what database you want to put information, what table, for example. And Kafka Connect, it's able to read from Kafka and to send it to the storage, okay? So it's a really fast setup because it's just configuration. Now, if we have problems here or in the storage engine, our producer doesn't care at all. Our producer only needs to understand how to send data to Kafka. And once the data is in Kafka, he can forget. It can forget because it's safe now in Kafka, and Kafka using Kafka Connect is going to retry until it's able to put that information in the cloud provider. So from the perspective of our applications, this setup, it's much better. There are also other benefits. Let's, for example, think we have different storage in the same cloud. So maybe we have here storage A, and now we have storage B. This is pretty common. For example, if storage A may be something like BigQuery, so it's like a data warehouse where our analysts and business people, it is just doing queries to understand the business. And storage B may be a more long-term storage like S3 or Azure Blob Storage. So our data science are there using Spark, for example, running machine learning models and things like that. Okay, so when that happens, what we can do is to have Kafka Connect reading for exactly the same topic in Kafka and sending the information to the storage B. Okay, that's perfectly possible, and because Kafka is able to make those both consumers, Kafka Connect and first one and the second one independent, it works quite well. But it also has some problems. And the main problem is in big organizations where there are many producers, many teams, and in many cases duplicated data. What we are doing here is to send in that information 2 times to the cloud. And typically the connection between our data center and cloud, it's very expensive. So now we are sending exactly the same information 2 times. So we are paying 2 times for the same thing. And that's something we try usually to avoid. So the ideal thing, it will be sending just 1 time, and from there being able to replicate the data to the different storage we may need, okay? So let's summarize with the slides and then cover that part. Better approach, we use Kafka Connect to send to the storage. So our producers are the couplet of the cloud services. If there are problems of connectivity, if there are problems in the cloud, our producer really don't care about it. The only problem we have in some cases when we are working in big organization or scaling this a lot is we are duplicating the blob, or sometimes it can happen several times. And that's pretty expensive and pretty inefficient. So how we can avoid that? It's with the next pattern. And this is my favorite thing because it enables a lot of things, which is we have the producer. Sorry. We have the producer. It sends the information to Kafka. Now we have again our cloud and Kafka Connect. But now Kafka Connect, instead of sending the information directly to the storage, is going to send it to a broker as Kafka. For example, PubSub. PubSub is the equivalent service in Google Cloud. You may think a Kafka version, but internally in Google Cloud, it provides very similar features, okay? Of course, we could use Kafka too, but in our case, we prefer to use PubSub because it's integrated with other cloud services. So it makes our life easier. But in other cases, we use Kafka. So that depends a lot of your use case. But as an example, let's use PubSub. So now Kafka Connect has a connector specifically for PubSub. So now we are sending our data to PubSub. And from PubSub, now using data flow, Dataflow is a framework to move data between places in streaming. So it's kind of similar to Kafka Connect, but it's coding. So it's much powerful, and you can do transformations, aggregations, filterings, and so on. And it's provided as a cloud service in Google Cloud. So using that, we can easily send our data to a database or storage. For example, in this case, BigQuery. The other one, which may be an object storage like Google Bucket. So now our communication is just not directly to the cloud. We have brokers in the middle. So we are decoupling all the different pieces, the producers, the consumers, and even the replication of data between clouds. And we try to do this in a centralized way. So we control always that connection, and we can make sure it's working properly and is used for all the teams in the company in a responsible way. And that's also a pretty important point. So based in this simple pattern, we start to build a much more complete platform to communicate different clouds and different data centers around the world. So what we have is a specific team looking at this and providing this as a platform to the other teams in the organization, and also looking for improvements to make it much more efficient. One of those improvements are compression. So compression is basically the ability in Kafka, Pulsar, and all those broker systems to compress the data in the producer and decompress the data in the consumer. So if we take a look to our previous scenario, we write another one. What we do is our producer is putting several messages together. So we have all the messages, small messages together. We put them together in something we call a batch, and we compress that batch, making it smaller. Now we send that batch to Kafka or to Pulsar or to whatever service. Our consumers read that batch, decompress it, and now they have access to the original messages. And this is super important because doing this, what we are going to do is to save bandwidth between our producers and Kafka. We are going to save bandwidth and storage in Kafka because those messages are going to be stored together and compressed. So we don't need so much storage in Kafka. And they are going to send to the different, or to the cloud, compressed. So we are also saving bandwidth in our cloud connections. And that's the most important thing because it's super expensive. The not so good thing is our producers and consumers need to spend some time compressing and decompressing the data. But that's a minor thing compared of all the other benefits. And that's why I always or almost always recommend to use compression to move data in streaming. Indeed, this is so important. Kafka, Pulsar, and the other brokers have specific possibilities to choose different algorithms. For example, you can choose set a leaf. This is a very popular algorithm. It's used, for example, in the Apache web server and many other places. The compression ratio is really good. So you are going to have smaller messages. The only problem with set leaf is it also requires a lot of CPU and some memory from the producer and the consumer to do the compression and the decompression. And because of that, we have other alternatives. For example, setstd, this is a compression algorithm from Facebook. It has a similar compression ratio to setlib, but it doesn't require so much performance, so much work in the producer and the consumer side. So it's like a more efficient. And if you really worry about the work in the producer and the consumer, then there are even more alternatives. Snappy, that this is one from Google. It's also very popular. It's more designed to achieve a smaller compression ratio, but it's more optimized for throughput because producers and consumers don't need to do so much work to do the compression and the compression. And there is even another one, LSL4, which is similar to Snappy, but it tends to have a better decompression speed. So it's not easy to recommend one or another one. What I recommend is to use compression. If you need to do this type of tuning, do some benchmarking with each of them to see what works better for your data, because they are highly dependent of your data. Depending on how it's organized, structured, what file format you're using, you may obtain different results. So it's always a good thing if you can spend some time doing a benchmarking with real data or similar to real data to see what is giving you the best performance and compression ratio. The other improvement we're working on is to use Schema Registry, okay? So what is a Schema Registry? So basically, we have our producer, once again, sending to Kafka. And we have our consumer. But we have most of the teams out there, most of the developers, I don't know most, but many of them use JSON. So they are sending JSON messages to Kafka. There are good reasons for that because JSON probably you already have the data in that format because you are reading from a Mongo database or because you are receiving that data from a REST API or something like that. But the problem with JSON is it's not very efficient. With JSON you have something like ID, one name, Tom, and you look to this is not efficient because you are sending a lot of extra characters, which a machine really don't need to understand the data. You are even sending the keys, which are always the same in each message. So instead of that, you could send something like one Antón. And this is going to be much more efficient because you are sending less data, right? You're sending the same data, but with less in a smaller message. So there are some formats you can use to do this. The most popular out there are Apache Avro and gRPC. Avro is from the Apache Foundation, gRPC is from the Cloud Native Foundation. They are binary protocols, so when you use them, the message is smaller. But the problem with this is in order to the consumer to be able to read the message, it needs to know in advance the schema, so how the data is organized. The schema is just a text file describing the different fields. This is the first field, it's an integer, the second one is a string. So when you are deserializing the message, the library knows how to do it, okay? So we could send to Kafka the message, the Avro message and the schema, but there is a better way. And that better way is using a component, an external component called a Schema Registry. So a Schema Registry is just an API, a REST API, which is basically what you're going to do is the producer before to send the message to Kafka, it's going to invoke this API to send the schema. It's going to retrieve an ID. This is just a number, I think 1. And now it's going to send to Kafka the number and the message. Our consumer is going to receive the number and message, is going to request to the schema registry, give me the ID, the schema with the ID 1, is going to return the schema, and now it can deserialize and use the message. So as you can see, it's much more efficient because we are not sending the schema in each message. We are only sending a number, and typically you are going to cache the schema in the consumer and in the producer side, so you don't need to do it for each request. There is also a benefit is in the schema registry, you can have some compatibility rules. So basically, if the consumer wants to evolve the schema, for example, the producer wants to delete some fields, okay, the schema registry can check if our consumers are going to be able to continually working because this is a compatible change. So for example, in this case, delete a field, it's not compatible because with the new schema, the consumer is not going to be, sorry, with the old schema, the consumer is not going to be able to read the old messages because now there is a field name, but it's not informed anymore. Okay, so with the schema registry, you can make sure your producers only make changes in the schema which are not going to break your consumers, and that's a really good thing. But this is exactly the same thing. You can see we have our producers sending to Kafka and registering the schema registry, and the consumers reading from it. Okay, there are different compatibility rules you can use, like a backward compatibility rule. So you are only going to allow to delete fields or add optional fields. You can have a forward compatibility rule, so you can only add fields and delete optional fields. You may even want to have full compatibility rules, so they only can add or delete optional fields, or you may have any, so you allow all the changes. Depending of what you choose, the old schemas may read the new messages, or the new schemas may read the old messages, or both things. Okay, so that this is very important to keep compatibility in big asynchronous architectures and make sure things work well. If someone needs to introduce a breaking change, what they have to do is to create a new topic and inform the consumers to go to that topic and to make the changes they need to avoid problems, okay? But in general, the schema registry is able to enforce that, and that's a good thing. So with all this together, we built this platform, and the motto of the platform was produce once, consume anywhere. The idea of our platform, it was an internal platform, is every developer in the company can produce information in, it doesn't matter where. So it doesn't matter if it's a particular cloud, it doesn't matter if it's a particular data center, it doesn't matter if it's in a different country, and they can put that information, that data in our platform. So it may be Kafka, Pulsar, Google PubSub, Microsoft Azure Event Hub, or Azure Kinesis, or AWS Kinesis or AWS MSK. It doesn't matter the technology, whatever is better for them. And we are able to do the governance of that data, to provide discovery in a self-service portal, and also to provide to everyone in the company the possibility to replicate the data to a different place using different technologies so they can read it and use it. And all of that with a self-service portal, so they really don't need to care how the platform is working under the hood, and all the problems and all the connectivity and all the technologies involved. They're just owners of their data, and they have a simple way to discover data from others and to request access to the data to be able to consume it. So this is like the produce once, consume anywhere vision we were working on. In order to do that, going further, we need to be able to replicate information and schemas between different places, different clouds, and different different data centers. Okay, so our first approach was to use something called a single primary architecture. This is basically, we have our Kafka in our data center, in one of our data centers. So let's call it the primary data center. And we have our producer in the data center sending data to Kafka. We have a schema registry. So it's registering the schema in advance and generating ID, for example, 1. Now we have a different data center, also with Kafka. We have now a consumer which wants to read that data. So what we are going to do, as we mentioned before, is send that data to this Kafka using Kafka Connect, but our schema registry doesn't know the ID 1, doesn't know what schema is the ID 1. So what we did initially was, let's replicate our schema registry in the other data center. So now we have ID 1 here. Our consumer can read the message with ID 1 and go to the schema registry and obtain the schema. And that works quite well. The thing is, now this data center is secondary data center because we cannot write, we cannot register schemas in this schema registry. If we do that, the schema registry will give IDG, in this case 2. But now, if someone is doing the same thing at the same time in our primary, it will have also an ID 2, and those schemas are going to be different. So we don't allow that. Okay, you can only write to the primary data center. And what we did is, instead of allow our producers to do it, what we do it is with a CI/CD service. So we have like a Git repository with the schemas, and each time you create a schema, it comes to the schema registry and do the registration in advance. This works quite well, but it has some important limitations. The first limitation is this only works if you have Kafka. But if you have different technologies, different services, it doesn't work because you can do the replication between the different schema registries. So for us, this was a quite important problem because we also wanted to work with some cloud technologies like PubSub, Event Hub, Kinesis, MSK. The other thing is, if we have a problem with the primary data center, one of our secondary data centers becomes the primary. So we have high availability. But when that happens, our producers need to know now they have to register the schema in a different data center. And that's kind of tricky to inform all our producers of those changes and make sure that they are like transparent to them, especially when we have producers, we need to evolve the schema dynamically. Things like change data capture, we mentioned it before, need to be able to register a new schema when there is a change in the database, when, for example, you add a new column to a table. So in order to do that, that becomes quite complicated. So we evolved this architecture from the single primary architecture to what we call an event mesh. With an event mesh, we have exactly the same thing. We have Kafka in the middle. And now we are sending the data to different places. So things like Confluent Cloud, which is based in Kafka, things like Kafka, Event Hub, or PubSub. But what we do here is instead of trying to replicate those schemas and have the same ID in every cloud, what we are going to do is each time we read a message and we send the message to the cloud, what we do is in advance with using a component called SMT, single message transformation, which allow us to introduce some customizations in Kafka Connect. What we do is we go first to the schema registry in the target cloud. We register the schema. It generates an ID only for that cloud, and we send the message with that ID and not with the source ID. So with this SMT, for every service, we are doing the transformation between the schema IDs in the source cloud and in the target clouds. And it doesn't matter if they are using a different technology or even a different format. For example, in the case of Event Hub and PubSub, they are not using a number, they're using a string as identifier, but we don't care about it because our SMT is able to, in a transparent way, to do the modifications on those things. So this worked much better for us because it allows to produce schemas in every cloud, and it only replicates those schemas or translate those schemas when needed. My conclusions: produce once, consume anywhere. It's a great concept. The event mesh, I think it's the way to go to replicate information between clouds. But it's yet not very mature. It's more for early adopters right now, in my opinion. If you stick to just one single vendor, like initially in our case was Confluent Platform, make things easier because you don't have to manage all those differences. So you can use the single primary architecture and some specific tooling to do it. But if you need to have like different technologies involved and work with all of them, it's yet possible, but some of those things are in preview. There are some tooling we have to develop by ourselves. There are different APIs in every schema registry, and you need to be aware of all the differences in the libraries, in the serializers and the serializers. So there is some complexity there. But it's perfectly possible, and I really think it's the way to go in the near future. That's all from my side. Thank you very much for your time. It has been a huge pleasure. If you have questions now in the QA, I'm more than happy to answer them. And if we don't have too much time, just feel free to ping me in Twitter or to send me a direct message on that network. I'm always happy to speak about this topic. Bruno, there is any question out there, or was just too much information?
It was not too much information, and there's no questions for now. But I have some questions myself. So you mentioned that you were not using JSON to send messages through Kafka. You were using Apache Avro or gRPC. Can you give us an idea on the amount of space that you save with that? So in rough numbers, how much in percentage will you save on size on those messages?
Yeah, that's highly dependent on your data, how you are sending the JSON file. So if you are sending the JSON files compressed, as I explained before, you are already, eliminating a lot of duplicated information. So the savings are not so big. But in some cases, it may be like 2 times smaller using Avro than JSON. That's one of the things. The another one is, another benefit you have is for the producer and the consumer, the serialized Avro, it's much more efficient than the serialized JSON. So you can have savings of around 30% or even more of CPU in the producers and consumers and some memory too, just switching to Avro. I think that's also an important benefit. The third one is with Avro, you can do all this schema management and have all those rules to make sure people is not breaking compatibility with their consumers. And that's also quite good. It's something you can do also with JSON schema, but in a synchronous architecture, it's yet a bit, not experimental, but pretty new. And it's not so mature as it is with Avro or gRPC. So in many cases for, big corps or big tech, it makes a lot of sense to move to Avro or gRPC. Because the savings can be quite significant.
Anton, we have a question from João Rebelo. He's asking if is the cost saving worth less human readability of all this schema management complexity?
Yeah, well, not an easy answer. That depends a lot of what you're doing. If it's a startup, you really want to iterate fast, you really don't care too much because you don't have a high throughput yet, JSON is perfectly fine. If it's just a big corporation, you're spending a huge amount of money integrating your services and in cloud cost, then in that particular case, go with Avro. It's going to be a very important improvement. Most of the places where I have been working on, thinking in big corporations, all of them use Avro for this type of things. And I really think it's the way to go. Of course, JSON may be good for you, but you are going to pay more in CPU, in bandwidth, and in memory. And if we are speaking here about a big scale, it's significant money. And it's no hard to start to work with Avro. It's true, you cannot open the message, but you can deserialize it. So you can use the typical tools you have, and observability, Kafka tools, and so on to see what is happening. So it's not like something just super complicated to do. And I think the benefits really worth it.
Okay, I think it's a wrap. We have no more questions, and our time has passed. So thanks very much, Anton. It was a pleasure to have you here, and I really liked and enjoyed the presentation. Thanks very much.
Thank you very much, Bruno. See you. Thank you.
Bye.